Welcome to Game Theory. This is the second in two videos on section 22 on the extensive form for general games. This video details two examples of the extensive form. The first example is with the game of two-card poker. So there are several rules for two-card poker. So with two players, A and B, each bet $1, giving a total of $2 in the pot. So the game starts out with $2 in the pot of money. So secondly, A chooses one card at random from a stack of 4 kings and 4 queens. A gets to look at the card, can choose to fold, which means that B gets the pot, so A comes away with 0 and B comes away with $2. Or A can choose to raise, which means that A bets an additional $1, adding the total pot to $3, and then B gets a chance to play. If B gets a turn, B can choose to fold, choosing not to play anymore, so A gets the pot, giving A $3 and B $0. Or B can choose to raise by adding $1 to the pot, and thus A shows their card. If A has a king, then A will win the game, getting $4. Otherwise, B wins the game and gets the $4. So when we're given this game, we want to develop our sense of rules. Given the set of rules, we want to develop our extensive form, because from our extensive form, we can start to get a sense of what the game looks like and how to analyze our form from there. So what we do know is that A starts off the game with a random draw. So our first vertex at the start of the game for our extensive form is a random node. So the first vertex, we have a 1/2 probability of a king, so we can indicate king and queen as a 1/2 draw, because there's a 1/2 probability for kings and for queens that A will get a king or will get a queen. So note that, just as in the description for extensive forms in the previous video, the sum of the outward edges probability adds to 1 for all random vertices, here indicated with a square, and this holds true. So if A gets a king or a queen, A has a choice. So A does not have an information set here, because A gets to see if it's a king or a queen. So A knows that's a king or a queen. So we can think of an information set as just containing the single vertex. There's only one vertex in that particular information set. So if A gets a king, A can choose to raise by adding $1 to the pot, or could choose to fold. If A gets a queen, A can also choose to raise or fold. Here, for ease of drawing, I'm going to indicate the folds on the inside line. And if A chooses to raise in either case, B gets a turn. However, B does not know if A has chosen to raise because A has gotten a king, or A has chosen raise because A has gotten a queen. So this constitutes an information set here, because B does not know the reasons why, or the previous moves. So B does not know if it's a king or a queen. This is where the lack of perfect information comes into play. So B can also choose to raise, to call in this case, or to fold. And in the lower case, we have the same moves. So fold and call. It doesn't matter the order so long as it's the same moves. So if A has a king and raises and B calls, then A has a total sum, so A wins. So A gets $4, but put in $2. So A gets a payoff of $2 and B turns out to have lost $2 for the game. If A raises and B folds, so following down into this vertex, in this location here, A wins because B has folded. But B is folded, so A wins $3, but they put in $2. So they have only won $1 from B, so B has only lost $1. So in this vertex here, if A wins a king and they folded, they've lost $1 and B has gained their $1. If A has won a queen and folded, they've lost $1 they've put in, and B has folded with that $1. B has gained that $1. If A gets a queen and raises and B folds, then A gets 1 point for bluffing and B loses their dollar. Otherwise, if A is called upon, A loses $2 and B gets $2. So with this situation, we can see how we can start to analyze this game. We don't know techniques just yet on how to analyze simultaneous games. In this fashion, we'll talk about analyzing subgames in the next section. But this is an idea of how to visualize a game that has both sequential and simultaneous information. Here, the sequential aspect of the game is where A gets to choose a card, and the simultaneous aspect is where B doesn't know which card A has chosen. The second game that we're looking at is where A and B get to choose whether to play Stag Hare or to play the game Prisoner's Dilemma. So they first must agree which game to play, and if they agree, then they play the game with the standard payoffs for that game. If they don't agree, then each player gets a payoff of 0. So it's to the player's benefit to agree on the game, because both players will then get a better payoff, or at least a good of payoff, because the standard payoffs for Prisoner's Dilemma and Stag Hare are all at least 0, if not better. So the standard payoffs for Prisoner's Dilemma and Stag Hare are shown below. But first, we have to decide how A and B are choosing to play. So A and B have to first make the choice simultaneously between playing Prisoner's Dilemma, here indicated as PD, or Stag Hare as SH. So if A and B choose to play Prisoner's Dilemma, then we can indicate that B has an information set here, because B does not know what A is choosing at a particular point in time. Player B just knows that it is their turn. So if player B chooses Prisoner's Dilemma at the same time player A chooses Prisoner's Dilemma, then both players will choose to play Prisoner's Dilemma. So player A will then have a chance to play that game. Move this diagram down. So player A will then choose to take their turn, and player B will also take their simultaneous turn for Prisoner's Dilemma. So with Prisoner's Dilemma, player A and player B can choose to cooperate or defect. And player B has the same choices, cooperate or defect. And then our payoffs we can pull straight from our table. So if A and B both cooperate, we have 2, 2. If A cooperates and B defects, we have 0, 3. Defect cooperate is 3, 0. And defect is 1, 1. If A chooses Prisoner's Dilemma and B chooses Stag Hare, then we have a payoff of 0, 0, here indicated in red. If A chooses Stag Hare and B chooses Prisoner's Dilemma, we still have a payoff of 0, 0. However, if A chooses Stag Hare and B chooses Stag Hare, then A now gets a choice of choosing to play Stag or Hare for the game Stag Hare. And B also has to choose simultaneously to play Stag Hare. So do they choose Stag or do they choose Hare? For those of you who don't remember, Stag Hare is a hunting game where players choose to either hunt stag or choose to hunt hare. And depending on if the payoffs would depend on if both players choose to hunt stag or hare. So stag is 3. Stag hare is 0, 2. Hare stag is 2, 0. And hare is 1. So if both players choose to hunt stag, then the payoff is greater for both players. If both players choose to hunt hare, then the payoff is greater for both those players. So when we look at this, each of the smaller sub-games, so if I were to look at each of these pieces here indicated in blue, this here, this Prisoner's Dilemma, is a sub-game. And this sub-game, also this Stag Hare game, will help us if we can analyze what's happening with the sub-games, then that will help us analyze what might be happening with the larger game. An analysis of the subgames does give us information about the larger game, and we'll talk about that in the next video when we talk about the normal form for general games. But again, analysis of the subgames gives us potential information, specifically about potential payoffs, such as Nash equilibrium points. So if you have any questions, please contact your instructor, and this PDF will be provided if you would like to take notes on it.